Okay, let us try to understand how do we implement the adder circuit, because adders happens to be one of the most important building block of any digital circuits in VLSI. So let us start with implementation of binary adders, and then let us see what are the significant performance parameters that we need to consider in case of binary adders. So let us start with implementing a full adder. So let us write the truth table of full adder. So this is a full adder circuit, so which is going to have inputs like A, B, C in. So it is going to have sum and carry out as the outputs. So let us write all 8 different combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1. Then you can take it as 1 0 0, 1 0 1, which is 1 1 0, 1 1 1. So these are the 8 different combinations of this particular input. So we can of course we already know, okay, this is a well-known truth table. Sum is equal to 0 if you have so this is 0 now, this is 1, this is again 1, and this is sum is 0. Okay, let me also start writing the carry. So carry out is 0 here, 0 here. Since it is 0 0 with a carry, sorry, sum 0 carry 1, sum 1 carry 0, again it is sum 0 carry 1, sum 0 carry 1, and of course for the last combination you're going to have sum and carry both of 1 1. So let us start writing the same truth table in a different manner. Okay, let me just write whatever carry out I have. So I can also write this in the form of carry status. So this is carry status. Okay, let me write it as, when I say carry status, so what is carry out compared to carry in? So for these two particular combinations, now we just group it into if you can see this 0 0 for both the combinations of A and B 0 0. If you can see, irrespective of the carry in, the carry out is 0. So I can say that the carry out will be deleted to 0 with respect to the value of C in, whether it is 0 or 1. If A and B are 0 0, so carry status is delete, meaning if it is 0 it will remain as 0, and if it is 1, this carry in will be deleted to 0 as carry out when A and B are 0 0. I will say this as delete. Coming to this 0 1, 0 1 or 1 0, if any one of the input is 1, here you can see in this case of in these two combinations, B is 1, in these two combinations A is 1. Whenever you have A is 1, B is 1, just have a look at this C out and C in. Can you see, whatever is this C in, same is the C out. Whatever is C in, same is the C out. Whatever is C in, same is the C out. This is C in, this is C out. Can you see now, whatever is the input C in, whatever is the carry input, that will be propagated onto the carry out whenever either A or B is equal to 1. So I will say this as propagate. So this is propagate. So what is propagated? This carry in is propagated to carry out whenever A or B is equal to 1. So any one of them have to be 1. So I will say this as propagate. So this is again propagate, this again propagate. Meaning to say, in the first two combinations where A and B are 0 0, irrespective of the carry input, carry out is 0. Now over here in these 4 different combinations, you can clearly observe that either A is 1 or B is 1 out of these 4 combinations. in this case, if you compare the C in and C out, they are exactly the same. They are exactly the same, meaning that whatever is C in is been carried down to C out. So that's why we call it as propagate. Coming to the last combination of 1 1 here, irrespective of the value of 0 and 1, you can see here it is generating. You can see this is always 1. So I will say it as generate. Now in this case, since the input is 0, you are generating a carry. This is generate. In this particular case, now there is already a carry 1, so it will be either propagated or generated. Of course, in this case it's actually propagated. So I will say this as propagate. So if I want to just combine these two and say, if the input is 0, it will generate the carry. If the input is 1, if the carry input is 1, it will propagate. So it is generate carry when A and B is equal to 1 1 and C in is equal to 0, you are generating a carry. If A and B is equal to 1, if C in is 1, then it is propagated to the carry out. So we are trying to now represent what is carry out in the form of carry in, depending on the value of A and B. So we know, of course, we know the expression for sum and carry. The general expression is sum is given by A XOR B XOR C in, and I can write carry as equal to AB plus BC in plus C in into A. So this is a generalized expression for this particular truth table. I can certainly write, okay, when do you get, of course, if I say this is D here, this is D here, this is propagate, and this is generate. This is generate. So when do I get a delete signal as 1? So delete signal will be 1. Delete signal will be 1 when it is A and B are 0 0. When A and B are 0 0, I will get a delete signal. So that's why I'll say D is equal to A bar B bar. Similarly, I will have a generate signal. So when do you generate a carry? So you'll certainly generate a carry when A and B's are 1 1. I will write it as AB. So when do you propagate a signal? You can see we actually propagated this C into this C out when A and B are dissimilar. That is A XOR B. This is the expression for delete, generate and propagate. Delete, when you get a delete signal as 1, so delete signal will be 1 whenever A and B are 0 0, meaning that your carry will be deleted to 0. When do you generate a carry? When A and B are 1 1. That's why it is A and B. When do you propagate the carry? When A and B are dissimilar. So this is the expression for delete, generate and propagate. This is the expression for sum and carry in terms of A, B, C input. We can certainly write the expression for sum as well as carry in the form of propagate, generate and C in. Meaning, if you want to write, of course, we know that sum is given by A exclusive, B exclusive, C in. Instead of writing this in the form of A, B and C in, I will write it in the form of this propagate, generate, delete and C in. So can I write it as P exclusive C in? So this is the expression for the sum of this full adder in terms of propagate and C in. Of course, how to verify this is, what is P is actually? P is actually A exclusive B. Suppose if you expand this P as P exclusive, A exclusive B, so it exactly comes down to this particular expression of A exclusive B is nothing but P and exclusive of C in is nothing but sum. So similarly, I can write the expression for C out. I can write the expression for C out as equal to, so when do you get a C out? It is whenever you generate the carry, then C out is equal to 1 and you have a propagate signal. You have a propagate signal and Cin. So suppose if you consider this particular combination, assume that okay, you want to verify for this combination whether carry out is equal to 1 or not. Since it is 1 1, since A and B are 1 1, my generate is 1 because this G will going to give me 1. So it is 1 plus of course this P is 0, P is 0, Cin is 0. Since it is 1 plus 0, so since you are generating a carry, so this C out is equal to 1. That's what you're getting. Assume that I want to do it for this. So if you want to get the expression for carry out in this form, so what is the value of G here? Because G is nothing but A and B, so here for this combination G is equal to 0. So this is 0 plus what is P? P is equal to 1. P is equal to 1. So for this particular combination, so this is equal to G is equal to 0. I'm just looking for this particular combination. Just have a look at this. For this combination, G is equal to 0 plus what is P? P is actually A exclusive B, which is equal to 1. But what is Cin? Cin is equal to 0. So it is 0. So this is now 0. So you can see now this is 0. So we can write the expression for sum and carry out in the form of propagate, generate and Cin. Meaning, instead of writing the expression for sum and carry in the form of ABC, it is also possible to write the expression for sum in the form of G, P and of course Cin. You can write the expression for C out in the form of G, P and the Cin. The sum expression would be propagate exclusive Cin. How about carry out? It is G plus P into Cin. P into Cin. So of course this is what I've written. So here this is the expression for sum and carry in the form of generate, propagate and Cin. Again it is in the form of C out in the form of generate, propagate and Cin. So this is the other way of writing the expression for the sum and carry. So we'll just move on to implementing a 4-bit full adder. So let me just try to implement a 4-bit full adder, 4-bit adder. 4-bit adder. When I say 4-bit adder, I'm going to use 4 full bit adders. This is 4 full adders. Let's say there are 4 full adders required. So that means to say I have inputs like okay A0, A1, A2, A3. I have B0, B1, B2, B3. So these are the 4 okay, 2 4-bit numbers I want to add it. Assume that you have something like okay, 1 0 1 1 and then you have 0 1 1 0. So now if I want to add something like this, okay, how do I proceed? And of course for everything you're going to have a Cin input, Cin carry in input, and of course the output would be you're going to have S0, S1, S2, S3 and there is a C out and there is an input something called as Cin. There is a carry in and there is a carry out, and of course you're going to have a 4-bit sum output. The implementation of this can be done using 4 full adders. So you can start writing the block diagram of those full adders. So now you have these 4 full adders. So this is my full adder 1, this is full adder 2, this is full adder 3, this is full adder 4. So this is my A0, B0, this is A1, B1, this is A2, B2, this is A3, B3. I'm going to have a Cin for this full adder. Of course I'm going to have some output and there is a carry output. Let me say CO1, and this is CO1 happens to be the Cin2 of this. So this is now the Cin. I'm going to have CO2. This is my okay S0. Okay, let me say this as CO0, this is CO1, this is now sum2, this is CO2, that is carry output second, this is 0th bit, first bit, second bit, and this is your CO out, this is your S3. So as we are supposed to get S0, S1, S2, S3, S0, S1, S2, S3, and the final carry is here. The final carry is here. Of course, we have these 8 inputs for this full adder, which is coming from A0 to A3 and B0 to B3, and there is a separate input which is carry in from a previous stage. Now, if you actually find out what is the time taken by this particular network to give the complete output, so let us consider this Cin is equal to 0. When Cin is equal to 0, what I'll get is, this is now 1, of course it is 0, 0, 0, 1. So this will be my output. You can see now, since the Cin is equal to 0, 0, 1 is 1, 1 plus 0 is again 1, there is no carry, 1 plus 1 is 0 with a carry 1, again we won't have 0 with a carry 1, again 1 plus 1 is 0 with a carry 1, this is your output. Now, if you carefully see the amount of time taken by this type of network to give the complete output, you can see all the circuit have some transistors for implementing all these logics. They all take certain time. So as soon as I give the input voltage, so I will get the output of each one of them. Suppose you can start straight away writing the inputs here. So if you start this as A0, you can see this is 1 here. So now this is 1, this is 0, and then this is what? And this is A3, this is 1 now. So let me also write it for B here. So what is B? So this is B of 0, it is 0, 1, and then I have 1 here, I have a 0. This is now Cin is equal to 0. So now as soon as I give this input, so let us assume that all the carries of this one, initially it is 0. So let us assume that this is 0 here, and this is 0 here, this is 0 here, and you have a 0 here. Now as soon as I give this input, so I will get initially the value of this output, because whenever I load all these values, they will going to give the output. So what is the output of this one? The output of this is now equal to, so let me write it, these are the initial values of the carryout. So will I get this as sum is equal to 1, and this carry which was 0, will it remain as 0? Because it is 0, 1, 0, so it will be okay, the sum is 1, the carry is 0. So whenever it is giving this as 1, so this will also be simultaneously doing the operation. So whenever this is evaluating this as 1, this also would have evaluated this value by taking this as 0, and because this is initially the value of this is 0, so is the output of this is equal to 0 with a carry 1? 0 with a carry 1. This is 1. This is 1 before, of course, simultaneously when you're doing this. So this is now 1. So how about whenever this is evaluating for 0, 1, 0, this was 1. Whenever it was evaluating for the first time, it is 0, 1, 1. So output is 0, this is 1. So now you can see you have a 0 here. You have a 0 in the previous case. This is now 0, 0, 1. So will you get the output as 1 now? This is, please don't consider this. This is the output that we'll be considering in the next case. Matlab. So whenever you actually input all this 0, 1, 1, 0, 0, 1, 1, 0, you'll get this particular output. Now you can see this is now 1. And then how about this? This is now 1. And what is carry output? This is the output you're going to get after a time t equal to t sum. So because after a time equal to t sum, does all the full adders respond to the available input at that instant of time? At the instant of time, the input for this Cin was equal to 0, this scene was 0, this was 0, this was 0, and all of them are so on. So I got this output, but this is not the final output. This is not the final output. So at t sum, this is the value. So this is not the expected value. You can see your expected value is totally different, and you are getting totally different value, because you, of course, here while doing it, what we did actually 1 plus 0 is 1 with a with no carry. Then 1 plus 1 is a 0 with a carry. You can see now we are actually making this to propagate. So whenever you actually evaluate for this third bit, you are supposed to consider the carry of this coming down here. So that we have not yet considered here, meaning this one which was evaluated for this 0 has to go now in the next case. Now what is the output now? So whenever this sum has reached here, so does this sum is equal to 0, 1, 0? So does this 0 which was there, has it now become 1? Because now this is 1. So how about this? This was 0, now it is still returning as 0. So does this now 0, correct? Because now this is 1, this is 1. So this is now 1, 0, 1. So 1, 0, 1. The output sum which was 1, now it will change to 0. So this has changed to 0. So what is the time that it has taken to propagate this signal from here to here? So now it is 0. So now carry has to actually propagate from this to this. Then how about this? So this was actually 0. So will that 0 become 1? This will become 1. But whenever this is evaluating this as 0, it is still considering this as 0 only, because at that time, okay, this was actually 1. Now this will become 1 now, and then we'll have it as, okay, now this is so this will take some time. So what I mean to say here is if you want to get the final output of 1, 0, 0, 0, 1 as sum and carry, it actually requires a maximum time. So when it is the worst case of this will happen when scene is equal to 1. When scene is equal to 1 and you have a combination of some case where you are supposed to generate a carry in the first full adder itself. If the first full adder gives a carry, this carry has to propagate to here, and then from here, and then from here. So total time that is required for propagation of the output is t sum plus t carry into n minus 1 bit, because this whatever carry you have has to propagate through 3 stages here. So since it is 3 stages, so what is the number of total bits here? This n corresponds to number of bits, which is in this case 4. Since carry has to propagate by 3 bits, so the entire propagation delay is given by t sum plus t carry n minus 1. The overall bottleneck of this 4-bit adder is what is the time taken by the carry to propagate from one stage to other stage. Suppose if the number of bits increase more and more, then the overall delay of your entire full adder network is going to increase. So if at all, if we want to reduce the propagation delay of this full adder, we have to somehow ensure that this t carry has to be reduced. If this t carry will, if you find that if it is get reduced, then the overall the propagation delay of the adder will going to reduce. So we have to always ensure that we have to somehow reduce the value of this t carry. So let us see, okay, how does this t carry can be reduced. So I hope, okay, this is fine here. So why it is t sum plus t carry n minus 4 is because once the carries are propagated through all these 4 bits, so it requires one more time of t sum so that you get the final output of whatever we expected it as 10001 for this particular combination. The worst possible time would be when you are T carry is when the input is 1 here, and then you have a favorable condition for this to generate, to propagate the carry. So this is the worst possible time. This is the worst possible time. So we will see in the next video how do we optimize the adder configuration so that you can reduce the value of T carry.